All right, so this is evaluating piecewise functions, and we're going to talk about end behavior too today. All right, so there's an opener, so you can go ahead and pause your video and try this on your own. This is from the previous lesson. All right, let's see how you did. So the directions here are state the domain of each function in interval notation. So remember, when you're looking at an equation, the first thing you ask yourself are there any restrictions? We know there's restrictions, or there could possibly be restrictions, if there is a denominator, because denominators can't be zeros, square roots, because we can't take the square root of negative numbers, or a square root in the denominator. That's a combination of both of those. All right, so let's look at the first equation here. So I asked myself, are there any restrictions? There's no denominator of this, and there's no square roots. Therefore, there's no restrictions. If there's no restrictions, my domain is all real numbers. Moving on to the next one, I see that there's a denominator. We know that we can't divide by 0, so I know that the denominator cannot be equal to 0. Solving for x, subtract 2 from both sides, and we get x cannot be negative 2. So now I want to write that in interval notation. If you have to do a sketch of what that looks like first before you write interval notation, that is fine. At some point, you should not have to do sketches anymore because you get used to doing them. So I have negative 2 here, and it can't be negative 2, so that's not part of my solution set. But anything less than and anything greater than. So now writing that in interval notation, that's negative infinity to negative 2 with the parentheses because it's not including negative 2, union negative 2 to infinity. Once again with the parentheses on the negative 2 because we're not including negative 2. All right. The next one, if you look, you have a square root here. So we're going to look at the argument, which is whatever's underneath the square root. That has to be greater than or equal to 0. It can't be negative. It can be 0, but it can't be negative. So we're going to say the argument has to be greater than or equal to 0. Solve for x. We get x is greater than or equal to negative 1. And now once again, if you want to do a sketch, you can. If you want to go right into writing interval notation, that's fine. So it can be equal to negative 1, so we are including that. But it's values that are greater than or equal to negative 1. So we have bracket, negative 1, comma, infinity. And once again, we're using a bracket this time because negative 1 is part of our solution set. Okay, last one right here is from a graph. So we're going to go look left to right because that's going to entail our domain values. So I'm going to start looking all the way from the left. And I see that it starts at an arrow pointing towards the left or towards negative numbers. So I'm going to say my x values start. I would be putting an air quote if I was in front of you right now because you can't start at negative infinity. Then I'm going to keep going. I still have x values here, but now I see that I've approached an asymptote and there's no x values there. So I'm going to say where there's no x values at. There's no x values at negative 3, but all x values leading up to that, union. And now I'm going to pick back up on the other side. It starts at where there are no x values, which is negative 3. Once again, a parentheses because there's no values there. And I look to the right, there's still values there. And then all of a sudden I realize that there's an arrow pointing to the right, meaning that it goes on forever and ever, so infinitely. Okay, that's it for the warm-up. Let's move on to the material that we're discussing today. So first we're going to talk about piecewise functions. Piecewise functions is not something that should be new for you. You did graphing piecewise functions, evaluating piecewise functions in Algebra 2 with trigonometry. So to remind you what a piecewise function is, a piecewise function is a function that is defined using 2 or more equations for different intervals of the domain. So if you look right here, if I covered this up, let me just use my pen. If I covered this up and it just looked like this, f of x equals 2x squared plus 1, that's one equation, right? But if you look at it, it's saying that f of x is 2x squared plus 1 if x values are less than or equal to 2. So if you're plugging in values that are less than or equal to 2, for example, 2, 1, 0, negative 1, you'd be using this first equation right here. Oops, I was trying to highlight this first equation right here, okay? All right, my second equation is f of x is just equal to 7 if you have the x value of 5. So if I say when x is 5, what is y? The answer is automatically 7. And then last but not least, I have the equation f of x equals x minus 2, and that's for x values greater than 5. So 5.1, 5.00007, 17, 45, 80 billion. I would use this second equation. I'd plug in that x value into, sorry, this third equation, I'd plug it in there. Okay? All right, so also remember this is called a piecewise function. And if you remember what a function is, for every input, so for every number you plug in, there's exactly one output. So when I plug in -1, because that's what f of -1 means, when I plug in -1 for x, I only get one answer. So a common mistake people make is they plug it into all three equations. You can't do that. You plug it into only the equation that number is part of its domain. So let's go look for this one. This one is f of -1. So I want to plug in -1, but the question is, which one of these three equations do I plug it into? So we're going to look at the domains. Is -1 less than or equal to 2? Is -1 equal to 5, or is -1 greater than 5? It's less than or equal to 2. All right, so we are plugging it into this first equation. So let's go ahead and do that. To find f of -1, we're doing 2 times -1 squared plus 1. -1 squared is +1. 2 times 1 is 2 plus 1 is 3. So f of -1 is 3. And this is just notation. If you just put the answer as 3, like if you're just like, here's my work, the answer is 3, that is also correct. Okay? All right, let's move on to the next one here. I want f of 5. So looking at my domains here, I want to know, is 5 less than or equal to 2? No. Is 5 equal to 5? Yes. I meant to change the highlighter color. So 5 is equal to 5. I am plugging into this equation. Notice it's the equation y equals, or f of x equals 7. You automatically get the output of 7 no matter what input you plug in. So the answer is 7 no matter what for this. So equals 7. All right. The next one, which is the very last one, f of 6. So plug in 6 for x. Which equation are we plugging in? Which domain does it fit in first? So if you look, 6 is greater than 5. So we're using this equation. And I do notice that we did use the first equation, then the second, then the third. That's definitely not always true. You just have to check the domain. All right, so we are going to plug 6 into the third equation. So to find f of 6, we are going to do 6 minus 2. So we get f of 6 is 4. Okay. All right. Another way of you can look at a piecewise function from a graph and find these values. So this is when x is -6, what is y? When x is 1, what is y? When x is -4, what is y? So on and so forth. So the direction state for the graph of the piecewise function given, evaluate each. Okay? All right, so let's go over to our graph. This is what it looks like. If you look at it, it is a piecewise function. Our first one is f of -6. So when x is -6, what is y? So we're going to look at where -6 is. -6 is right here, okay? And we want to look at what is y then. So we're looking for the blue pieces of the graph. If you look right here, when x is -6, y is 1. So when x is -6, y is 1. And you can just box it like this, or you can put equals 1, whatever you want to do, okay? All right, f of 1. So f of 1, so when x is 1, what is y? So here is where x is 1. Now, some people accidentally say there's two answers. They'll say, oh, y is 1 and y is -2. That is incorrect because there is no, oops, I didn't mean to do that. There is no value right here. That is a hole in the graph. Well, it's a removable discontinuity, which we'll talk about later, okay? There's nothing there is what that's saying. There is, however, something here. So when x is 1, y is -2. All right, next one, f of -4. So when x is -4, what is y? If you look, that's an asymptote. There's nothing there. So since there's no answer, we are going to say that it is undefined at -4 because there are no y values at -4. All right, the last one, f of 5, when x is 5, what is y? So here is where x is 5. What is y? Once again, there are no y values. This right here is an open circle, an open point. It means there's nothing there. So, and there's no other points anywhere else. If there was a point right here, the answer would be 3. But there's no points anywhere else. So it is once again undefined. Make sure you look at the difference between 5, f of 5, and f of 1. There is a value here. There is nothing here, and there's no other points at 5. Okay. All right, let's move on to this word problem here. So it says, it gives us a situation, and we want to write a piecewise function. Okay, so it says a store charges $15 per t-shirt for orders of $50 or fewer t-shirts. I lost my place, sorry. $13.50 per t-shirt for orders of 75 or fewer but more than 50 shirts, and $12.50 per t-shirt for orders of more than 75 shirts. Write a piecewise function, write a function, which is going to be piecewise because there's 3 situations, that represents the cost, C, for X number of t-shirts. So instead of using X input, Y output, we're using X input, C of X output. All right, so let's write our equation. Instead of doing Y equals, we're doing C of X, the cost is equal to. And now if you look, there's 3 different outputs. It could be $15, it could be $13.50, or it can be $12.50. So that's 3 different situations, I should say. Those aren't my outputs. So I have 3 equations. I'm going to bind them together with this grouping symbol. All right, so I'll start with the first sentence. It's $15 per t-shirt. Remember, number of t-shirts is X. So this is 15X. And that's if. And it says for orders of 50 or fewer. Okay? So I could say that's 50 or less than 50. But I can't, I also realize while I'm saying this out loud, like could I buy -6 shirts? No. So really it's in between 0 and 50 shirts. So I'm going to write in between 0 and 50 shirts. So this says in between 0 and 50 shirts. It says less than 50, but greater than 0. Now I just have to make sure I don't need it or equal to, okay? So let's think about this. Can I buy 0 shirts? Yes. So that's or equal to. In this situation, does it include 50? So I got to read it in. It's 50 or fewer. So that means, yes, that includes 50. All right, my next sentence is $13 per t-shirt. So that's, $13.50. So 13.5x, or you can do 13.50x, same thing. If, and it says for orders 75 or fewer, but more than 50. So this is in between 50 and 75. So now I'm going to write in between 50 and 75. That says less than 75, but greater than 50, right? And now once again, I have to decide if I'm putting greater than or equal to, less than or equal to, or less than. All right, so it's for orders 75 or fewer. So this is including the 75. And I already know before I continue reading, this can't be an or equal to. Because if you think about what that would look like on a graph, it'd look like this. And that's not a function because it doesn't pass the vertical line test there. So it's not going to include it, but it says more than 50 anyways right there. It says more than 50, so that's not including 50. All right, last but not least, $12.50 per t-shirt. And that's if orders more than 75, right? And it's not 75 to infinity. It's just more than 75, right? So we're going to say X is, and it's more than, so greater than 75. All right, there's my piecewise function. All right, so last thing we are going to talk about is writing end behavior. You wrote end behavior in Algebra 2 with trig looking at graphs and doing other things, looking at equations also. So we are going to do it by looking at equations today, and then we're going to create our own end behavior on graphs. So how we do this is we do this in limit notation. We get more into limits at the end of the school year, but just so you have an idea, limits are the concept of approaching a value without necessarily ever reaching it. That's called a limit. So if you're headed towards the y value of 6 from the left and from the right, that's the limit. But it's the y value that you're heading towards, okay? That just explains it in this box here too, if you want to look at it further. So it says, given the graph of f of x, write the end behavior using infinity notation, which is what you guys used in Algebra 2 with trig. Then write it using limit notation is what we use in pre-calculus. Okay? All right, so we're going to do it how you used to do it first. So you can say like, oh, yes, I remember this. So you're going to look at this graph, and how it used to look in Algebra 2 with trig is it says as x approaches negative infinity, f of x approaches what? So what you're going to do is you're going to look at your x values as they get smaller. So if you're looking at your x values getting smaller, physically with your eyes, you're looking towards the left, okay? So you're looking this direction, right? And you're going to say what's happening to the y values. There's 3 situations that can be happening. Your y values can be going up, that's towards positive infinity. Your y values can be going down, that's negative infinity. Or your y values can be leveling off. And if it's leveling off and it looks like a horizontal arrow, then you say what y value it's leveling off at. Okay? All right, so let's go ahead and look at this first one here. So I want to know, as I look left on my graph, what's happening to, so as my x values get smaller, looking left on my graph, what's happening to my y values. If you look, there's an arrow pointing up, so that's approaching positive infinity. And you can just write infinity. You don't have to write positive infinity. All right, this next one says, as my x values are approaching infinity, or as my x values are getting bigger and bigger and bigger, or as I look to the right, what's happening to my y values? So I look here, what's happening to my y values? They're pointing downward, so they're going towards negative infinity. Makes sense? All right, so that's what you did in Algebra 2 with trig. This is how we write it in pre-calculus. So this says the limit as x approaches negative infinity of the function f of x, what's happening here. So it's saying this says as your x values are getting smaller, what's happening to your y values. And it's just a notation, okay? So we look as our x values are getting smaller, our y values are getting bigger. I erased it instead of circling it, but that's fine. So that's positive infinity. And as our x values are getting bigger, that's what this says right here, as we approach infinity or as we get closer and closer to infinity. So to the right, what's happening to our y values? They're going down, so that's negative infinity, okay? So this was just fill in the blank, but from now on, you're going to have to write this, okay? All right, so let's go ahead and practice that 4 times. So all of these are given the graph of f of x, so I named them all f of x for you. They could be named something else, like one could be g of x, and one could be p of x, and so on and so forth. Find each end behavior using limit notation. So that's what your directions are. Find the end behavior using limit notation. All right, so we're going to say the limit as x approaches negative infinity of f of x is, and now you're going to say what's happening as your x values are getting smaller. So look left on your graph. As your x values get smaller, as you're going towards the left, there's an arrow pointing up. So they're approaching positive infinity. And we're going to do the limit as x approaches positive infinity of f of x. And so that means we're looking to the right. As we look to the right, or the right end of our graph, there's an arrow pointing down. So that means it's approaching negative infinity. Not too bad, right? The new notation you got to get used to, but it's easy. All right, let's try another one. We're going to do the limit as x approaches negative infinity of f of x equals. And we're also going to do the limit as x approaches positive infinity of f of x equals. Now, I do understand that this is being done on an iPad, and you can totally copy and paste for the next 2. But for your notes here, when we're first starting it off, you should get used to writing the notation, because most of the points come from the notation and then just saying what's happening, right? All right, so we're going to look left on our graph as our x values get smaller and smaller. So this end, if you look, that arrow is not pointing up. It is not pointing down. It is leveling off at a y value. So we're going to say what y value is this leveling off at? If you look at it, it's 2. We're going to look right as our x values get bigger. That's an arrow pointing up, infinity. All right, next one. limit as x approaches negative infinity of f of x equals, and the limit as x approaches positive infinity of f of x equals. All right, the left end of our graph, arrow pointing down, right end is another arrow pointing down. So this is negative infinity and negative infinity. All right, last but obviously not least, limit as x approaches negative infinity of f of x. Limit as x approaches positive infinity of f of x is. All right, we're going to look to the left on this end. That's not pointing up. That's not pointing down. It's leveling off. So the question is where is it leveling off at? What's this y value? -3. Same thing here, not pointing up, not pointing down. What y value is it leveling off at? The same y value. It could be two different y values. -3. Okay, that's it for end behavior. The very last thing is sketch a graph of a function that has the following end behavior. So what if I was doing this and just giving it to you and I walked around the room, I would expect no one's really to look like anyone else's because there's so much interpretation of what can happen between those two arrows that you're drawing. Okay, so I'm going to start by drawing my ends. So this one says the limit as x approaches negative infinity. So this is my arrow on the left-hand side. That's approaching positive infinity. So my arrow on the left-hand side is going to be pointing upward. And then the limit as x approaches positive infinity of f of x is 3. So my arrow to the right, my right-handed arrow, is not pointing up, it's not pointing down, it is leveling off at 3. So if you see where 3 is, it's right here, okay? I'm going to have an arrow that's leveling off there, and it can be leveling off above that dash line that I just drew or below. And I definitely want to erase this dash line here, okay? It was just there to so you guys can see what I was doing. And now I want to connect those two ends together. I can connect them however I want. I just have to make sure that this is still a function, meaning it still has to pass the vertical line test. So the easiest way to do this is to just literally connect them like that, right? But someone else could say, well, I want to go like this, and then I want to have it come up like this, and then it's still approaching -3, right? Or sorry, +3. But I like the first way I did it, so I'm just going to leave it like that. All right, last one. So my end behavior towards the left, if I'm looking with my eyes, is approaching negative infinity. So downward facing arrow. And then same thing for my limit as x approaches positive infinity of the function, downward facing arrow. So once again, I want to connect these two arrows however I want to. I can make an easy downward facing parabola like so. I could get crazy and go some loops like this and say this is what mine's going to look like. But what I don't want to do is be like, I like cats. Oh, that's not a cat at all. I like flowers. This is what mine's going to look like. Okay? Yeah, that's a flower. You heard me. Because this is not a function. Okay? Why is it not a function? It doesn't pass the vertical line test. So don't go overboard here. Okay? Just make sure you're still making a function. There we go. There's mine. All right. That is all for today. You can go ahead and start your homework.